Okay, here we go for Module 5. Is there a question? All right, the hydrosphere is what it's called. I guess I could turn this on for y'all. You can see it.
Funny.
All right, so is that what it says at the top of your book here? We're at like 5A, the hydrologic cycle is what it says at the top. Lab 9, what page is that?
2020.
20, page 20. All right, you see the word hydrosphere coming up here, yeah? So we know what a sphere is,
Circle.
all right? Well, a sphere, so three-dimensional circle. And what's hydro?
Water.
Water. Okay, so we're talking about all the water. Now, we've been talking about water for a long time, right? And all the parts of the atmosphere. So we talked about air for a while. Now we've been talking about water for a while. And then eventually we're going to put those two together, have air and water, which is going to end up with weather, right, when we're looking at weather. Okay, so we're on Lab 9. Here we go. Many people call the Earth the big blue marble. From space, it looks like it's very blue. Guess why?
All water.
Yeah, there's a lot of water on the planet Earth, okay? So I think it's 72% of the Earth is water. And we're going to be looking today at the different kinds of water. Like a bunch of that is salt water, right? Because the oceans. So we'll be looking at that. Let's start with an introductory video.
This is a view of the Earth as it is seen from the surface of the moon. No wonder astronomers call it the blue planet. Now, if we look a little closer, we'll see where this blue comes from. Here we see a close-up of the Earth with a satellite in the foreground. Underneath, you see an ocean. That, of course, is where Earth gets its blue color.
Oh, well, that was nice and short. Okay, so from the ocean. So the hydrosphere is the sum of all water on a planet, solid, liquid, and gas. Those, by the way, are the phases, solid, liquid, and gas. Did y'all get that on the quiz?
Mm-hmm.
Oh,
Yeah,
okay.
I did, but I didn't know if you were asking for like specific as in like liquid as in water, solid as in ice, gas as in mist or steam.
It would count either way. Yeah, sure. So what is the hydrologic cycle then? It's the process by which water is continuously exchanged between the Earth's various water sources, okay? So it's water recycling process. So all the water we have on the Earth has all been recycled. And it always continues to be recycled. So when people talk about running out of water, we're not running out of water except possibly in one particular spot. For instance, if we're in a place that's having no rain, then we could be in something known as a drought.
So it's running all the water on the planet.
Yes, the sum of the all the water on the planet.
For hydrologic,
Notice it says on a planet. We're talking about the Earth. What's the question?
is on the where it says hydrologic cycle. Do I just put the water recycle process?
Yep, that water recycling process. I have it underlined there. You can just write that part down if you like.
Yeah, that is cool. It says on
It does say on a planet, yeah. So, as far as we know, all of the planets we've been able to study in any kind of detail, mostly the planets in our solar system. We have not found any liquid water on any of them. Maybe we found frozen water on Mars. We're not exactly sure, but it's possible. But we haven't found liquid water anywhere, and that's a requirement for life as we know it. All right, let's see. Another video.
The hydrosphere is actually the sum total of all of the water that exists on planet Earth. That water is stored in a variety of sources. The vast majority of that water, more than 97%, is stored in the Earth's oceans. Of course, the oceans contain salt water, not fresh water, so the vast majority of the water in Earth's hydrosphere is not even drinkable. Most of the rest of Earth's hydrosphere is fresh water, and therefore it's drinkable, but it's locked away as ice, because slightly more than 2% of Earth's hydrosphere is in the form of glaciers and icebergs. Most of the rest of the fresh water in the hydrosphere, more than 0.5% of the hydrosphere, is also not very accessible because it's underground. This groundwater is usually not visible, but we can see it here because it is being released in a geyser. Less than 1/100th of 1% of Earth's hydrosphere is contained in the lakes, rivers, and streams that we normally think about when we think about water. Believe it or not, if we add up all of the moisture that is soaked into the ground, we have almost half as much fresh water as what is contained in the lakes, rivers, and streams of the Earth. The rest of Earth's hydrosphere, about 1/1000%, is contained in atmospheric moisture, such as clouds and humidity.
All right. So we're going to be looking now at table 5.1. We are going to look at the Earth's water sources. All right. First of all, oceans. So you can write down oceans. Is oceans already written for you?
It doesn't. This is the majority of Earth's water. Oceans.
Okay, let's see. Yeah, the majority of Earth water is in the oceans. We have glaciers and icebergs. I don't know why mine doesn't say that. Oh, yeah. You can say for that the majority of Earth's water, 97.3%.
We're going to write 97.
Yeah, so on majority of Earth's water, say oceans, 97.3%.
Or you mean fresh water?
No, all the water of the Earth. Now the next blank that says, where's the majority of the Earth's fresh water? The majority of it is in glaciers and icebergs. So glaciers and icebergs, 2.05%. So what is the largest source of liquid fresh water? That is groundwater.
What is the glaciers?
2%, 2.05. And then 0.685 is the groundwater. I should have those on there. Sorry about that.
0. What?
0.685.
What's
0.685%. So a small amount, right? Groundwater. 2 point, what did I say? 2 point what? Oh, 5%. And 97.3. All right. So we cannot drink ocean water. Don't drink ocean water, in fact. Now, surface water that's not in the oceans, whatever we've got left going on there, and soil moisture is where we'll have the rest of it. Okay, so in those two things right there, and an atmospheric moisture. So whatever's left over after these is what's in those. Okay, so the smaller amount right there. Yes?
Can we do the question right
Yes. Okay, y'all have those blanks filled in?
Yeah.
All right. There we go. So, oh, here it is. Here's our percentages. The majority of the Earth's water is in the oceans at 97.3. The majority of Earth's fresh water is stored in icebergs and glaciers, 2.05. The largest source of liquid water is groundwater. Who has a well? Anybody have a well that you get your water from? I get my water from a water company called Aqua Water.
Same.
Yeah. So,
Well,
you have a
I
well?
believe.
Okay. Where do you get it? Where's that water coming from?
Brown.
Underground, right. So you're tapping in to the groundwater right there. And so Aqua Water probably gets the water from a river and then cleans it and puts it up in the water towers and that kind of thing. So that brings us to the hydrologic cycle. Do we have a question? Question? Okay, hydrologic cycle. All right, so like I said, that's all about the recycling of the water that's on the earth. Okay, so we go from liquid to gas to liquid. There's solid in some places. Right here we see some ice right there. Okay, so we see the liquid water, gaseous water in the clouds, and solid water in the snow right there. We're going to go through this in a lot of detail in just a second. We're going to watch another video, however.
So many videos today.
Did I stop?
The hydrologic cycle begins with evaporation. Water evaporates from the various lakes, rivers, streams, and oceans of the planet, and the water vapor travels through the air, eventually forming clouds. The clouds then form rain, which we call precipitation. That precipitation falls on the ground. Some of that precipitation just runs along the ground. Other precipitation is absorbed into the ground. The precipitation absorbed by the ground can either be absorbed by plants and re-emitted into the air through a process called transpiration, or it can simply run into the nearest body of water as groundwater flow. If the precipitation is never absorbed by the ground, it simply runs along the ground into the nearest body of water. We call that surface runoff. Now let's put all of this together. Evaporation. Precipitation.
He didn't say
Soil moisture. transpiration, groundwater flow, surface runoff.
All right, there we go. So we're going to write down in your blanks now about the shuns, okay? All these end in T-I-O-N-S, so the shuns right here. The first one is transpiration. That's the evaporation of water from plants. All right, turns out that plants have these little holes in their leaves called stomata, and the water can leave through there if there's enough water in the plants. So you've noticed this on a hot summer day. If you go to stand under the shade, it's much cooler under a shade of the tree than under the shade of, say, a pole barn or something like that. And that's because, honestly, the trees are releasing like a tiny mist of water onto you the whole time. Okay, so there's like a mist of water coming out. So it feels so much cooler. That's why it's so pleasant under a shady tree.
That's amazing.
Yes, and part of that also is helping to keep the water being pulled up through the plant as well. So it sort of creates that, I hate to use the word vacuum, but it creates that space where water can be pulled up through the roots right there. If we are in a large drought time, then the plants will tend to hold on to their water a little more, so that the transpiration will be decreased at that point in time. But for the most part, they are constantly letting out some of the water they don't need. They're also using those little holes to let air in, and they're actually letting CO2 in and letting oxygen out, and so we can breathe it. Yeah. Evaporation is the process in which a liquid turns into a gas. See the word vapor in the word evaporation. Vapor. It's turning into a vapor. But y'all already knew the word evaporation anyway. Our next shun is condensation, the process by which a gas is turned into a liquid. Okay, it's a gas that turns into a liquid. You've noticed this also on a hot summer day if you have a glass of lemonade with ice in your glass, and you'll notice the outside of your glass gets all wet. Okay, that's condensation of the warm air hitting the cold glass and turning the water that's in the air turns back into water that's liquid on the side of your glass. So it's not leaking out of the glass or anything. Okay, next comes precipitation, water falling from the atmosphere. It can fall as rain, snow, sleet, hail, anything that is bringing down water from above. When we get into our units on weather, we'll look at each one of those individually. It seems like there might be something else. Freezing rain is another one. Next comes distillation. Is your word distillation in there for y'all?
Yes.
Okay, distillation is evaporation and condensation of a mixture to separate individual components. All right, this is actually something we're going to be doing in our lab today. You may have heard of distilled to distilled. Have you heard of distilled water? Yeah, distilled water is treated so that anything that's not water is taken out of it, mostly minerals and things like that. And typically that's done with filters and things like this, but we're going to use a combination of evaporation and condensation to do that. Next comes percolation. That's the process by which water moves downward through the soil down to the water table. So if you have a well at your place and you have a pipe going down into the ground to get access to the water right there, it's moving down toward what is known as the water table. There'll be a place down there where the water will be stored, and you can get to it by putting a pipe down there and using a pump to bring it up. Is that all the shuns? I feel like we've lost a couple. Transpiration, evaporation, condensation, precipitation, percolation.
And distillation.
Yeah, distillation is a little different. It's not really happening in nature so much. I mean, I guess it can, but there's an experiment, that experiment 5.1 in your book. It says, write this up on the back. You must have a lab page there. We'll do that for lab in just a minute. We'll be doing a distillation lab here in just a little bit. But we got to finish the lecture first. Okay, everybody got your shuns written down? Cadence, you still working on it?
Yeah, I took a picture. I'm only on the last one.
Did you got the whole thing? Okay, great. All right, residence time is how much time is the water spending in any specific area, okay? So the average time a particle will stay in a system. So let's say we're talking about a raindrop, a drop of water. That drop of water is going to stay in various locations. I have a little chart for you here in just a minute. And so, you don't write anything just now. Wait till I come up with the next slide here. So which system has the longest average residence time? What system has the shortest average residence time? And you're going to fill in the residence times in your lab manual based on this. Okay? So, a drop of water will stay in the ocean for approximately 4,000 years. That's a long time. All right, it'll be locked up in glaciers and icebergs for 1,000 years. So think about a drop of water in the ocean. If it's down deep in the ocean, it'll stay in the ocean a long time, right? It's only going to evaporate once it gets to the surface. How does it get into the ocean? Rain drops it in there. Icebergs and glaciers for 1,000 years. Groundwater, 2 weeks to 1,000 years, depending on how deep in the ground it goes. Soil moisture, 2 weeks to a year. You know this, sometimes we'll have some humid days. Did y'all have any rain this morning?
Yeah.
As I left my house, it was raining, like raining hard. And then by the time I got here, I don't live very far away. By the time I got here, there was no rain.
There was no rain. We lived 3 minutes away.
I live, maybe 10 minutes away, but I was really surprised. And you know those days, like a summer day after it's rained and you feel like that steam coming out of the ground? It's because that's evaporation of the rainwater that was in there. Okay, it's evaporating there in the soil moisture. Atmosphere, about 10 days. How does it come out of the atmosphere? Rain.
I definitely feel moisture in the air in the morning.
Yeah, on these humid days for sure.
I like wake up and do my hair and everything, and the next minute I'm like, stop.
Well, that's why I walk out and I get rained on my hair. I'm like, oh, no. Yeah, so. Lakes about 10 years. Rivers about 2 weeks. Rivers are typically flowing, moving, so therefore the water is being turned more easily. And then swamps, depending on the activity in the swamp, if it's typically swamps are kind of not much motion going on, right? They're kind of stagnant. And so probably between 1 to 10 years. All right, so you understand what residence time means? It's how long that drop of water will stay there on the average. Not every single drop, but on the average. All right, so this is on page 112 of your book for those different water sources. All right, so we're looking at ocean here. This would be the longest time, right? In the ocean. How long did we say? How many thousand years? Was it 4,000?
4,000 years.
Yeah. So this is definitely the one. Which place has the longest residence time? The ocean, for sure. All right, and there's a beautiful ocean scene. Oh, so speaking of the ocean, we know that the ocean water is salty. So when we look at it, we're going to see dissolved ions and chemical salt. So you know that ocean water is salty.
Right there.
It tastes salty, right? Are we saying salinity right there? Yes. Hold on. Wait till the next slide. Okay. So you can see right here. Here we have pure water in here. Notice there's a few little ions floating around in there. There's nothing really. There's no such thing as pure water, really. There's always going to be a little bit of something in there. Like the water you get out of your faucet has some minerals in it, depending on where you live. It may have some chemicals in it, depending on who your water treatment plant is. So I have aqua water, and aqua water treats the water with something called chlorine. And you know what the chlorine does? It kills any microorganisms that might be in there. That's good. We don't want to get microorganisms in our water because it might make us sick. Okay? Some places actually add fluorine or fluoride to the water as well. Fortunately, aqua water does not do that. I don't want to be drinking fluoride. It's poison, but it's supposed to make our teeth strong. So that's why they put it in there, to make your teeth strong. And so it depends on where you're getting your water from. So here it is in this middle picture right here, drinking water from the tap. So this first beaker right here might represent distilled water that you get in a jug from the grocery store. Water from the tap. Now, I don't want to dissuade you from thinking that that stuff in your water is not good for you. It's actually very good for you. In fact, I have a water filter at my house called reverse osmosis filter. Have y'all heard of these? Reverse osmosis. It goes to this long, under my sink, It takes out all the minerals. Because some of those minerals include chlorine, and chlorine is toxic, but it's better than drinking microorganisms, right? So water companies basically have to do that. So my water system, my filter system, takes those things out. I have to add minerals back into my water so that I'll get them. So you know how I add minerals to the water I'm drinking right here? Went through a reverse osmosis system, and I added minerals back to it. And the way I did it, when I take a jug of water, I add a little bit of salt in there. So I actually add salt back into my water. I can't taste it. It doesn't taste salty. Just a little bit. There are minerals that are in there. It's
When
that
you
pink.
add salt to your water.
Uh-huh. It's that pink Himalayan salt. You can't taste it. Yeah. But it gets the minerals back in here. Ocean water, however, is very salty. And don't drink ocean water. It's not good for you.
And that's why I asked it there.
sometimes accidentally we'll get some in there, and little kids will, and they'll get some into them. But if you are like, say you're shipwrecked and you're on a little boat or whatever, and you're really, really thirsty and there's water all around you, don't drink the salt water. You'll die more quickly.
I remember.
We'll talk about that in a minute. Yes.
I think I was younger. I can't remember. I'm pretty sure it was a lake or maybe the ocean. But I got it in my mouth, and I ended up in the hospital.
Uh-oh.
And I
For
was
what?
a baby.
For what purpose? If it was fresh water, it may have been like an infestation, like a amoeba or something like
I
that.
think it was amoebas. Not amoeba. I don't remember. I can't remember. If
It
was
would
a
have given
lake.
you a really bad upset stomach.
I think it was that. Maybe it was a lake or the ocean, but I drank like a lot of it. Like my parents said, it was like the first time I ever been to the beach or something.
Oh, yeah.
And they put me in the water, and they said the first thing they didn't even like, 'cause, when you're a baby, like they hold you and stuff. But they didn't know how I got it in my mouth. But obviously, I got a bunch of it in my mouth, and it ended up in the hospital for a few days. But
For a few days. Wow. Okay.
yeah.
Well, and so there could be a couple of things. There's this thing where, like, say you have a little child who likes to, like my little grandkids think it's fun to drink the pool water. Well, I have chemicals in the pool water to keep the pool water from turning green, right? So that chemical actually causes there to be a change in your body chemistry. And so you have to be very careful like that. So there's a couple of things can happen. I can have my pH thrown off, it can make me feel sick, this kind of thing. Or I can actually have so much water in the system that it'll end up in your lungs, and you can drown without being under the water. It's very strange. Yeah, so it's important not to drink a whole lot of water from other sources like the ocean or even pools. All right, here's where you're going to write down your salinity question right there. The measure of the mass of dissolved salts in a given mass of water. That is salinity.
All of that, or is there?
You can say the amount of salt in water. That's the easy way.
Amount of salt in water.
Yep. Notice I have salt in quotations, that because depending on where you are, the salts might be different. Most of the time the salts are sodium and chloride, just like we eat on our food, that's table salt. But sometimes they're potassium chloride, sometimes they're magnesium chloride, depending on where the salt's coming from in the world. The average salinity of seawater is 35 grams per kilogram. Have y'all ever seen a saltwater fish tank? Like at the dentist up here, they have a really big saltwater fish tank. They're usually they have beautiful fish in them, but it's super important for somebody to manage that fish tank so that it has the proper salinity.
Oh wait, what?
You're just still on the same thing.
Oh, we're not doing what is the average of.
It is. The average salinity of seawater is 35 grams per kilogram,
So
if
count
it's asking for that.
35 grams.
35 grams per kilogram. All right, so if we look at all the salts, you can see here that our seawater is 96.5% water, H2O, and then this little bit right here is the salts that's in there. So mostly chloride and sodium. So sodium chloride, that's NaCl, that's table salt. So this is for most of the seawater, but we also have magnesium, calcium, potassium, sulfates, and then minor things in there. So depending on where in the world you are, I think the Pacific Ocean is mostly sodium chloride, but some of the smaller places like the Dead Sea and other saline lakes like that have more magnesium chloride than sodium chloride. Yes?
Where the heck do we get, like, we have the ocean, right? We don't have, wait, I'm pretty sure we have like salt in the lake, but not like as much. I
There
don't
are
know.
such things as salt lakes like the Great Salt Lake.
But like in Bachelor Lake, there's no salt.
No.
Okay, but how
All
does
fresh
it get
water.
in the ocean? How does salt get, like someone just like drops
Eventually,
salt
oh, how does the salt get in the ocean? That's a good question. We're going to get to
because
that.
of sand?
Yeah, it comes from the land. All right,
Oh,
we're going to see
this-
here. Yeah,
Oh,
the
okay,
salt
okay,
is
I
on the
know.
land, and it's getting washed into the ocean,
So after
and
it
it
years.
stays there. Okay, that's what our lab's going to be today. We're going to see how that when we evaporate the water, the salt doesn't go with it. Okay, the salt stays in the water right there. So,
does it get
in
worse?
fact, we're going to see how actually the oceans are getting saltier and saltier as we go. Did you have a question, Zoe?
That's what I was gonna
Okay, yeah, they get saltier. So-
Eventually, it will make us so sick that we can't like, get in the ocean if we.
Yeah, I would say eventually. Yeah, eventually it'll be too salty for us. Let's see.
Like we can't even dip a toe in it.
Since the
Do that.
No longer
oceans
than that.
contain more than 97% of the Earth's hydrosphere, it's not surprising that they're large. In fact, almost 70% of the surface of the Earth is covered by oceans. On average, these oceans are about 97% water, 2.72% sodium chloride,
On average.
and 0.78% other salts. Now please understand what I mean when I use the term salt. When you talk about salt, you're talking about table salt, sodium chloride. Now that is a good part of what's in the ocean. However, when a chemist uses the term salt, the chemist is referring to a broad class of compounds which dissolve in water. So when we say that the oceans are made up of salt water, we're saying that the oceans are made up of water that has a broad class of chemical compounds dissolved in it. Of course, salt water is not the only thing you find in the oceans. The oceans are also teeming with life. One of the most majestic creatures you'll find there is the whale. Whales are mammals, and another kind of mammal you can find living in the ocean is the dolphin. Whales, dolphins, and most of the other creatures who live in the ocean have been specifically designed to live in salt water. Indeed, if I took one of the creatures that lives in the oceans and put it in fresh water, it probably would not survive for very long. In the same way, if I took a freshwater creature and tried to put it in one of the oceans, it probably wouldn't survive for very long either. So the oceans and the creatures that live in them have been perfectly designed for one another, a great testament to the power and majesty of the Creator.
I have a
Alright.
question about
Yes.
dolphins.
Mm-hmm.
We all know that like if you're a dolphin, like a shark is scared of dolphin. We all know that.
A shark is scared of a dolphin?
Yeah.
Is that what you said? Okay.
We all know that, right?
Well, it depends on how big the shark is and how big the dolphin is.
Why are sharks scared of dolphins?
Well, I will say dolphins
They
are
don't have
crafty.
teeth, like,
They do have teeth,
well,
but they don't
have,
attack,
Like, yeah,
and they won't eat a shark. Yeah. So the deal is that they're kind of crafty. What I mean by that is that
No,
dolphins are smart.
Well,
And they
they're
can
really
outsmart.
smart animals.
They can outsmart a sort of a dull shark. So sharks are fish and dolphins are mammals. So they're different classes of animals
So
altogether.
sharks are so basically sharks are like tough and brave but stupid.
Not too
And
bright,
then
and not that
dolphins
they're
are
stupid.
like weak, sort of.
They're
but
not
very
weak.
smart.
They're pretty. They're just very smart.
But
And so they can outwit a shark. So I don't know that a shark is afraid of it. A shark just doesn't. It's too much bother.
that's why sharks are in SeaWorld.
bothers them. Yeah. What?
So that's why sharks are in SeaWorld. Also, they probably eat someone. But
Yeah. I haven't been to SeaWorld in so long. They definitely have
they took away
dolphins
Shamu.
there.
Like Shamu's not there.
It's gone. But they still have dolphins.
Yeah, but I heard they took him away because it killed 2 people.
Oh, well, that's a
What's
reason to take them away.
You don't know
It's a killer whale.
You don't know who Shamu is? He's like the most famous SeaWorld at sea. Like Shamu is SeaWorld.
Well, I've never been to SeaWorld until this Saturday.
You're coming? This coming Saturday?
Yeah.
Very
That'd be
cool.
fun.
Well,
The
apparently
SeaWorld's-
Shamu's not there anymore.
Yeah.
Shamu was kind of the general name of a
Yeah, he
orca
has like a big thing
or
in
killer
the
whale.
water.
Yeah. So.
It's like a shark.
All right, but back to our salt. So this right here is a picture of the world. So the gray stuff you're seeing right here, that's the land masses. It's kind of hard to see. But see, there's South America, North America, here's Texas. On the left side, you can see Africa, Europe, and Asia. Here's Australia. So what is this is showing here, the darker the red is, the more saline you'll find in the ocean. So let's go to the Gulf. Here's the Gulf of Mexico right here. It's pretty dark red in there, isn't it?
Oh yeah.
So that tells us the Gulf of Mexico is pretty salty. And one of the reasons is because it is kind of enclosed in that Gulf area, like that circular area there. So therefore it,
So red is really salty.
yes, red is very salty, and then purple is not very salty at all.
Wow, there's some. Ooh, up there.
Yeah, so this is the Mediterranean Sea right above Africa. I don't know what's so purple right there, but that, I think that's the North Sea up there. It's very cold, but it looks like it's not very saline up there, very salty up there. And then yellow here, the Great Lakes are clear. The Great Lakes are here. They're not saltwater. And this right here is called something Bay in Canada. What's that? St. Lawrence Bay. Yeah, Kate, just put the phone away. All right. So you can see obviously in the darkest red areas here, including the Gulf of Mexico, right there. All right. Now this guy is in a place on the earth. Let's see if I can find it real quick.
Oh yeah, it's like so much, there's no salt at all.
No, it has a lot of salt in it, is what it is.
But as if you drop something in there, it doesn't sink.
It's just so small. Yeah, this is the Dead Sea. It's in Israel. Now the Dead Sea there's water flowing into it, but it doesn't flow out anywhere. Okay, so the water doesn't go anywhere. It stops right there. And so all the salt that's in there has no outlet. It doesn't go away anywhere. And so he's not sitting on anything. He's not sitting on the bottom there. He's not sitting on a float. He's just floating in the water. So it turns out there's a density situation. When I have more salt in the water, then it makes the water more dense, and therefore lots of things can float in it. So we
if
have
I jumped in there and like I just float back
you
up.
can sit straight up. Yeah, it's hard to actually dive down into it because the water keeps buoying you up.
So I can just like lay there.
So this is a guy had a hypothesis. He was wondering, had a question about stuff floating in the Dead Sea.
Hi, I'm Eric Trinidad, and we're here at the Dead Sea in Israel, where we're going to answer the question that we've all been wondering since biblical times. Will a 14-pound bowling ball float in the Dead Sea?
Do you think a 14-pound bowling ball will float in the Dead Sea?
I'm gonna say no.
The Dead Sea has attracted visitors for thousands of years, and today it's a popular destination for tourists who come to cover themselves in therapeutic, mineral-rich mud. They also come for the novelty of floating in the water, because there's so much salt in it that many things become unusually buoyant.
Tell me, do you think a 14-pound bowling ball will float in the Dead Sea?
Yeah, I think it's possible. I'm not really sure. I don't know.
I
It could go either way.
About 31% of Dead Sea water
This
is
is all
comprised
salt.
of natural salt. This makes the Dead Sea denser than ordinary water by about 17 to 24%, depending on the data you find on the internet. This means that a 14-pound bowling ball could float in the Dead Sea, but not in a tub full of bathwater,
To the bottom.
or at the beaches of Israel along the Mediterranean, or in a swimming pool outside the old city of Jerusalem. Or even in the Sea of Galilee, where Christians believe Jesus walked on water.
Has anyone ever tried to do this before?
Not as far as I know. Never with a bowling ball.
What do you think?
It's floating.
It's definitely floating. So that person's not sitting on anything.
It's
So-
not even hard for her to like sit up. She's just like.
Well, because like she'd have to keep her neck like that, yeah. So, but anyway, that's very, very salty water, and you become very buoyant in very, very salty water. We have very salt water in America called the Great Salt Lake in Utah, and it's not quite as salty as the Dead Sea. It also is a body of water that has no outlet. The water doesn't go anywhere from there, and so therefore all the salt collects up in there
Why do
and
they put
gets
mud all over
saltier.
themselves?
Well, so then the mud, so Cadence was asking if the water was clear. The water's very clear. And the reason it's very clear is because nothing lives in there. It's the Dead Sea, right?
So
What
there's
makes
sharks,
our
no
water
fish.
all murky and stuff is the creatures living in there, all the amoebas
So
and all that
no
kind of
fish
stuff.
or
No
anything.
fish. Now there is a little bit, we think there is one particular type of microorganism that can live in there, okay? So, but it doesn't bother anybody. But I do know that I had a friend who went and she said when she came out of the Dead Sea, it felt real slimy on her skin afterwards.
That's
And
good.
furthermore, if you had any little cut or something on you, yeah, once you go in there, you know it. When you go in that water, ooh, because you can feel that salt
That
in there.
mud is great for your
So the
skin.
mud has lots of minerals in it, and that getting minerals on your skin is supposed to be good for you. Okay, so getting mineral intake. And so you'll even find people around here selling mud from the Dead Sea and selling salt from the Dead Sea. It's supposed to be all, very healthy for you. This kind of
Yeah,
thing.
because everybody's skin is gonna be on it.
What about it?
Everybody's skin is gonna be on it.
Well, so yeah, I don't know how they harvest it. I'm sure they clean it or whatever. So.
Hopefully.
All right, so how does the salty ocean support creation science? So Cadence was asking earlier, won't it just keep getting saltier? Where did the salt come from in the first place? So it turns out the salt in the ocean came from the earth. So let's take the Great Salt Lake in Utah, for instance. Okay, so that, like I told you, is a lake that doesn't have an outlet, only an inlet, so rain and then other rivers will flow into it. But there's an area right next to it called the Great Bonneville Salt Flats. So the earth is actually salt. And that salt flows into the lower spots. That would be the rivers and going into the Great Salt Lake. They don't flow out, so the salt stays there. So salt going into the ocean had to come from the land. Okay, so it came from the land first. So The main salt is sodium chloride that we find in most oceans, and all the oceans and most of the other salty places. And so the idea is, if you do the calculation of how much salt should be in the ocean, then if the Earth is millions and millions and millions of years old, like evolutionists scientists want to tell us, there would be a lot more salt in the oceans. They'd be so salty that it would probably upset the life that's found there. So really, even though the oceans are getting saltier every year, they're not as salty as they would be if the Earth were millions of years old. Do you get what I'm saying? Yeah. And so it actually kind of supports the idea of a younger Earth. If I'm going to err on any side of this, we don't know how old the Earth is, but I would probably, my best guess would be that it's a fairly young Earth. And when I say young, like 20,000 years old, something like that, versus millions and millions. But once again, that's just my opinion. All right, it could be millions of years. God may have made it millions of years and then put life on it. That's up to him, right?
Or do you think he originally had life on it, like dinosaurs and stuff? Like
Oh, I believe in dinosaurs, sure. I believe they got destroyed in the flood.
I thought it was an asteroid.
Yeah, well, some people say that. Some scientists say that. I think that after the flood, the weather changed. You know, for instance, all the moisture was in the sky until it all fell out, and then all of a sudden people said, "Oh, there's blue skies up there." Noah said that, right? And so it changed the atmosphere, and so some animals were not supported.
Sky at first.
It was just almost like it was cloudy all the time.
That would be nice. I think it's cloudy.
Well, very humid and cloudy all the time.
If I was a dinosaur.
I like a nice blue sky myself. So, but I think we'll get to that when we talk about the weather and how that could have changed over time. Okay. All right, so if the Earth was as old as the evolutionists say it is, then the oceans would be much saltier due to surface runoff. So here we go. Here's the continent. The salt's coming from there. So the salt's going in from the Earth. And the input, about 450 million tons per year. The output, only 27%. I think this output here is talking about the ocean, the salt we are taking out of the water. We'll take some salt out of the water. You know why we take salt out of the water?
So we don't die.
Well, no, so we can sell you salt in the grocery store.
Oh, I do that.
Yeah. So anybody here use that pink Himalayan salt? Yeah, they get it from a different location with a lot more minerals in it, so it's healthier for us. So I use the pink Himalayan salt as well. I use the white salt right here.
Yeah, we use.
I'll use that for science class. Yeah. So
We
it's
use
cheap.
salt. Well, okay, we use Epsom salt or like whatever salt.
That's
there is.
magnesium sulfate. Yeah, or magnesium
Like
chloride.
my dad was great regular like salt stuff like that or something. Whenever my Nana comes along, she like has to buy us the pink Himalayan salt.
Uh-huh.
She thinks it's better. So.
I think it tastes good personally. So, all right. So what did it say here? Here it said upper limit 62 million. All right. So that's still a long time. Upper limit. It could be the Earth could be 62 million years old, but I think evolutionists think it needs to be even older than that to support the mechanism for the life that they say was created here. All right, this right here, we're looking at icebergs and glaciers. This is actually a glacier.
So you can slide down it.
You could, except it's very kind of rocky in there. It's hard to tell from here. I will tell you that this is fresh water that's frozen, that's there for a long time. Gravity's pulling it down. It's sort of like a frozen river. So it is moving, it's just moving slowly. And then every now and then these crack off, and what are those called?
Iceberg.
Icebergs. So icebergs come from glaciers, and therefore icebergs are fresh water.
Wait, is that lake frozen?
The lake is cold, but it's not frozen.
So
No.
wait,
This is probably salt water down here, and then this freshwater ice is floating. It floats really well because of the salt water
Could you
being so
slide
dense.
down it?
Can you what?
Could you slide down it?
Well, when you say slide, it's rougher than it looks. See how rough it is?
I would love to
Yeah.
slide down
So maybe
that.
if you had a really good sled, that wouldn't fall down in those cracks.
I still would not. That would be
Yeah.
so uncomfortable.
Because those cracks right here are called crevasses. You can fall down in them and people get lost in there. So you want to be careful. But if it were possible, like right here, it looks a little more smooth right here, doesn't it? So maybe you could slide down there. But keep in mind, this is very cold, and if you land in the water, it's very, very cold.
My
All right.
butt would hurt.
So this is flowing. It's just flowing very slowly. And what's causing the flow? Gravity. Gravity's
So like a
pulling it down.
volcano.
It's slower than a volcano. Volcano, you can see that movement. If you're talking about lava flow,
Yeah.
you can see that. This you can't really. I mean, you stand there and you can hear funny noises like, these little cracking noises of the stuff, and then you can see them fall off. We'll talk about that. That's called calving, in fact. Calving. It's you just ignore it. That's fine. So when glaciers and icebergs, they're packed snow, it gets compressed into sheets of ice in the mountains, and when it breaks off, gets to the end, the gravity will finally pull it down. That's called, I don't know why it's called calving. Isn't that also what it's called when a baby cow is born? Isn't that
What?
called calving?
No, it's called, that was milking.
I think it's called calving, yeah. So when a large chunk of ice breaks off of a glacier and falls into the water, creating an iceberg, are you supposed to write that down?
Oh, let's just ask what is Calvin?
Calving would be the creation of an iceberg from a glacier.
So wait.
When part of a glacier breaks off to form an iceberg.
Okay.
We're going to watch a video on it. I think people will go on trips in a ship, you know, to see this. Just go watch.
Glaciers and icebergs contain a little more than 2% of the water in the Earth's hydrosphere.
That's really dirty.
This is the Mendenhall Glacier in Alaska. As you can see from the video, a glacier looks a lot like a river of ice flowing down a mountain. In fact, that's what it is. A glacier is a massive collection of ice whose weight is forcing it to flow down a mountain until it encounters water, where it then floats. Eventually,
There it is.
stresses in the ice cause large chunks of the glacier to break off in a process called calving. The broken pieces then float in the ocean as icebergs.
That's so dangerous. I could
Uh-huh.
kill someone.
Okay, so here's another one.
Oh my goodness.
There's a guy right there.
Yeah. Get out.
No,
All right.
That was not smart what you did at all.
People, they go on trips in order just to do that. People would take them on tours of glacial caves. Yeah, so I know it's a little scary to me. Once the glacier is gone, melted, so with global warming, which is natural, we're in a warming trend right now, that's completely natural, it'll leave behind some features in the earth, like this. A glacial trough is a U-shaped valley right here, and then up on these mountains you can see where they're pointy. We have things called horns, that's the top of the mountain, and tarns are like these little ponds that are found there. Sometimes those stay frozen, in fact. We can have hanging valleys like this one, resulting in a waterfall coming off of there, all from glacial work. Okay, can salt water freeze?
Yes.
Yes. In fact, in your book there is a little lab, if you want to do it at home, where you can get some salt water, put it in the freezer, then you'll taste it, and you'll see that it is salty.
It says, what is fern?
Fern is frozen salt water. A dense pack of old snow is what it
We
says.
do frozen
So here,
salt
no,
water.
that's wrong. Here's what it is: a dense pack of old snow. So for salt water to freeze, it has to be colder than 32 degrees Fahrenheit. So you have to be pretty cold. Your freezer gets colder than that. Your freezer gets down to, I think, about 4 degrees Fahrenheit. So fern is a dense pack of old snow, and it ends up looking, so remember, snow would be fresh. It looks like that. So you can see the lines in it, almost like we're looking at Grand Canyon or something, right?
What is it called?
Fern, F-I-R-N.
It says,
Yeah. What is frozen seawater called? It's called sea ice. So can ocean water freeze? Yes, as long as it's really, really cold.
yeah, it says, can salt water freeze? And I said yes.
Yes, and now the question is, what is frozen seawater called? It's called sea ice. Here's a picture of a little penguin walking along on sea ice. Remember, sea ice is salt water, but icebergs are fresh.
Aren't they fast swimmers?
They're very good swimmers. I don't know if this is all made up, those little foot tracks on there, if that's just CGI or something like that, but it's pretty cute. Groundwater, after glaciers, icebergs, the largest source of fresh water is the groundwater flowing underground. You can see here somebody's house with a well that's got a pump that pumps the water up to their house. Look, it's closer to their garden right here. It's not as deep there. They go to the deeper, probably better source down there. And you can see right here where you can see that what's called perched water. There'll be spots. See this dotted line right here where it says the water table? Beneath there, underneath here, there's saturated zone. There's water all through there, but there's also rocks and things like this. So to get down to it, you'll have to have a nice filtered pump down there. Yes.
It says water table, like as a blank.
Okay. Yeah. So our water table. Let's see if I have it. Okay, I don't.
How
So the
high
water
is-
table is the depth at which the water is found. So it's found in different locations. Like at my house, I have a lot of mud, and then my mud makes my water table stay kind of high, but the water's very muddy there, so it's not really great for a well.
How long would it take to dig a hole to the center of the earth? Like,
Oh, to the center of the earth, we can't do it.
you can't?
No, it's impossible. Yeah. The deepest we have got, we'll talk about this later in this class, but the deepest we have gotten in the earth is 7 miles deep in the Kona borehole. And it used, when I was growing up, it was 1 mile deep, but now we've gone 7 miles.
Why can't you go any farther?
It's very hard to get a drill bit that's longer than 7 miles long, you know what I'm saying?
Yeah.
So it's hard to actually have the machinery to do it.
And I guess, with someone down there, like 7 miles deep, and
And it gets hot because you're getting close to magma and stuff like that. All right, so the water table is the level at which the water is, depending on where you are. Some of it's deeper, some of it's not as deep. Soil moisture, okay, the soil will hold on to some water for a while, but it'll evaporate fairly quickly. Remember, its residence time was pretty short. All right, what's this? Here we go. All right, plants and their soil. You can actually drown a plant if you put too much water in their soil. Y'all probably know that already, right? All right, yay, we get to do our experiment now. I have to go get some water from the sink right here. We're going to be looking at a demonstration of distillation. And does the water cycle actually do this process? And the answer would be no. This is a little project you may want to try. I thought this might be kind of fun to do at home, where you can take a Ziploc bag and show the different shuns. So the water, we put water in here, big ground water. We have evaporation, condensation, precipitation, surface flow. Here, this is transpiration. Here's some more evaporation right there. And then we should have percolation, which is the groundwater going down there. Okay, so is that the end? Yeah, that's the end. All right, I'm going to stop this recording.